Hello and welcome to this machine learning project titled Forecasting Sales in R with Time Series Models and Stochastic Gradient Boosting. In this video, I'll give you an introduction to the problem that we're trying to solve and the data set that we'll be working with, as well as some of the method that we'll use to create our forecasted values. So let's jump right into it. First, here's an introduction to the problem. A retailer wishes to forecast total POS, which is point of sale, for several of its stores for the coming month. And so we'll be given data provided at the store level with various features from the retailer. And so we'll have the total POS value that we'll see in a minute, which is just a sales number for the store, and then a couple of other, or a handful of other features about the store. And then we'll assume here that sales are impacted by internal store events like promotions and holidays, as well as external market events. And just like anything, there will be some of that that we have data for and we can account for in our models, and there will be some things that we don't have data for and we can't account for in our models. So we'll talk a little bit at the end of the project about kind of how that plays out in our forecasted values. So let's look at the data here. And so it's a relatively compact data set. It's a time series data set, meaning the observations are time stamped and are equidistant apart, and they occur in sequential order. So in this case, the variable is going to be week. And so that's our timestamp variable, and we can see that each of these observations in the data set are a week apart. We actually split here between observations 139 and 140 to a different store. We can see the store number changes from 559 to 426. And in fact, all of these have data that end the week of September 28th, 2012, and then we'll be forecasting the next 4 weeks after that. So it'll be the month of October of 2012 will be the window that we're forecasting, the 4 weeks of October in 2012. So we have time-stamped transactional data that creates a time series. We have our dependent variable, which is total POS, and again, this is in dollars. And then we have a few other variables just telling us some things about the stores themselves. And so we have store number and format and square foot and store holiday. So let me give you a little bit more detail on what all of those entail. But this really is all the data that we'll be working with. And with just this small amount of data, we can create some pretty accurate predicted values that we'll see. So again, the data set variables, just to have it written out for you. We have the week, which is our timestamp. We have the store number, which is just the retailer's store ID number. That's not a quantitative value. It's just a classifier. And then we have the store format. It happens that there are 3 formats in this data set. We have blue, green, and red. And again, that's just another classification variable. And then square footage, which gives us the total square footage of the store footprint. So that tells us how big the store is in physical size, which of course we can assume affects the amount of sales it does. And then again, total POS is our dependent variable. And then store holiday is an indicator telling us if that week is a holiday for that particular store. And so obviously some weeks are holidays and some weeks are not. So that's a quick rundown on the data set, and of course, as we're programming against that, we'll kind of dig into a lot more of those features in more detail. For our modeling, the approach that we'll take is an ensemble model, and so we'll actually use 2 different methods and then create a combination of those forecasted values. The first method, or the first model we'll use, will be the best time series model, and that'll be determined by a holdout MAPE. Now MAPE is an error metric. It's a model fit statistic. MAPE stands for mean absolute percent error. And when you're talking about time series data, transactional data like that, MAPE is really the standard error metric that you would go with. You tend to get away from the RMSEs and those sorts of measures and go with MAPE. Model 2 will be a best stochastic gradient boosting model determined by holdout MAPE. And this might seem like kind of an odd application. If you're familiar with gradient boosting techniques, this might seem like a sort of an odd scenario in which to use gradient boosting. And it is typically on a on a data set that's relatively small in the world of machine learning. Gradient boosting might be seem a little bit too powerful or a little bit too complicated, but it has a nice application here. One is it gives us a little bit different view of the data from the time series models, because as powerful as time series models are, they do have some holes in them. So introducing another modeling method to combine with the time series models just gives us a different look at the data. But also just for learning purposes, this is a nice application to see just the way you need to think about interacting with data. The same data set, the different shape that the same data set has to take on when you think about creating the features that you'll use for your models. And so we'll see here that the data set for the time series models is very straightforward, but when we want to use it for gradient boosting, it takes a little bit of processing to get that in a format that we can use for a boosting method. So those will be our two methods, and then our final model, our final forecast value, will just be a weighted combination of those. And so we'll take the outputs from Model 1 and Model 2, we'll assign a weight to each of those, and I'll show you a real simple way to determine a weight that's at least a good starting point. And that'll create our final predicted models. So just a bit more about the time series models. We're going to use those to capture things like autocorrelation, seasonality, and trend. We'll do two different time series models. One is an autoregressive integrated moving average, so that's known as an ARIMA model, and then also an exponential smoothing model. And so these are, if you've ever been around time series forecasting, these are kind of your bread and butter different models, kind of basic time series models. And so whenever we do those, we'll forecast each store individually. And so we'll take the time series for each store, go ahead and fit the best either ARIMA or ESM model, and then we'll see which of those two are the best for that particular store. And as we'll see, some of them it'll be in ARIMA and some will be in ESM, but we'll take that one as the champion time series model. And then for the stochastic gradient boosting method, we'll use that to capture linear relationship and to introduce cross validation. The one big drawback for time series models is validating your model is pretty difficult, just because all of the data, you're assuming a lot of correlation in the data points. And so when you start pulling them out to run validation tests, cross-fold validation tests, it's a little bit trickier than just doing some of your standard K-fold cross-validations or even jackknife methods or anything like that. So we'll be able to introduce cross-validation by using a boosting technique. Whenever we do the boosting model, we'll actually forecast all the stores simultaneously as part of one giant data set. So as opposed to stripping the stores apart and handling them one at a time, we'll lump everybody in together and then let the store variables be features that we introduce in the data set. But again, we'll talk a lot more about that once we get into it. So that's going to do it for this video. In the next video, we'll actually jump into the data set and start programming against it and really look at what we've got and what kind of cleaning we need to do before we get into any of the modeling.